And it's official. It's week 7. Welcome back, everyone. We're almost to our midterm week, week number 8. And so that's our pretty much our bigger announcement for the day. Exam 2 is going to be next Tuesday. So if you're in the in-person section, it'll be an in-person exam, just like you did on exam 1. If you're on the online section, I did exactly what I did for exam 1. I've emailed you through the Canvas messaging system. Excuse me. Okay, I've emailed you through the Canvas messaging system here for instructions on scheduling your exam with either the Pocatello Testing Center or the Idaho Falls Testing Center. So if those instructions are missing in any way, if there's any kind of problems getting those things scheduled, contact me right away and we'll get it sorted out soon enough. I'll probably send out another reminder for scheduling the exam on Thursday as well, but pretty much it's just going to be a complete redo of what we did on the first exam. Any questions at the moment about the upcoming exam 2? Okay, well, it's going to be these 5 sections right here. 5 sections right here. 1.5 was looking into the matrix equation, things about parametric vector form. So those would be the major topics. 1.7, we were looking into linear independence, or you know what? That's starting to get foggy. What was 1.7 actually? Let's take a look here. 1.7, yeah, linear independence. For some reason, it just seemed like too many sections there. So we're looking at linear independence, linear dependence, related theorems. 1.8 to 1.9 are both about linear transformations. And 2.1 is about matrix operations. We're not going to get into sections 2.2 on the exam, but we still have to run through these notes for the sake of the week so we don't fall too far behind. One thing I did forget to do, just for full disclosure, is I'm putting a formula sheet on the end of all of our exams, and I meant to have this available sooner when I published the sample exam problems. I only just noticed this on Monday when I was writing exam 2 that I forgot to actually put this out. So see this document when you're studying for the upcoming exam 2. The list of formulas and theorems is going to be this sheet right here. Just a reminder, you don't have to print this out. This is not going to be something you have to provide. This is literally the last page of the exam. So I'll have the good old theorem 4 available. That's one we get a lot of use out of. Some definitions, the core definitions of independence and dependence. So if you lose your way, if you're a little stressed out in the exam, you can see this core material for those core definitions. Quick definition on linearity and the fundamental theorems about 1-to-1 and onto. So this doesn't tell us how to do all the problems, but if you forget issues of rows versus columns and those kinds of things, this will be helpful material. But really, just like before, it's going to be problems quite similar to what you've been doing on the homework exercises. So a good way to review is making sure you're caught up on all these sections right here. I don't have a late policy, so a week got really busy, maybe you didn't get section 1.8 in, I'll still accept it for full credit. In fact, that's probably the number one thing that you should do to study for this exam. Get caught up on all the sections as fast as possible. And just like on exam 1, my objective is to get all this graded as soon as possible so that I can provide you with that feedback ahead of that exam. And even if you're turning in material in person on paper, I'll be scanning it and emailing it to your ISU email address on Friday or potentially later in the weekend, the feedback on that homework set. But that's my generic comments about the second exam. Any last questions at all, folks, before we return to section 2.2? Okay, let's get started then. We just basically peeked at the notes and drew some things in. We looked at the analogy to see how the new definition is going to match our intuition. The goal is to find the inverse of a matrix when it exists. I do have a big revision here because apparently counting was hard. My examples are all scrambled. My revisions are the numbering on the examples were off. They were actually off by a lot. One of them was right, only example 5, and then just about everything else was off. So sorry for that distraction there. Only just noticed that today when I was going over the notes again. So the idea about a matrix inverse is the same idea with the multiplicative inverse in the field of real numbers. A number 5, because it's not 0, has an inverse, 5 inverse written this way, because 5 times 5 inverse results in the multiplicative identity 1. So we're trying to match that By finding the inverse of a matrix A, we seek a new matrix C, so that when we pre-multiply by C and post-multiply by C, we get the identity matrix, playing the same role as as 1 right here. I times any matrix, if it's defined, results in that matrix. So it's much like multiplying by the number 1. But one thing we have to be kind of careful about is when we say multiply by a number, say 3 times 5, it doesn't matter if you visualize that as 3 times 5 or 5 times 3, because multiplication is commutative. This is not true with matrix multiplication. There's going to be properties that we'll discover where commutativity of multiplication does work out. The inverse turns out to be one of those cases. Until we know we have the inverse, it's good to have this concept. Multiplying here is called pre-multiplying. Because the matrix C is in front of A, and multiplying C here is called post-multiplying. Because the matrix C is now towards the right. And that concept turns out to be critical to get things just right in certain situations. We'll see on these notes here. So the identity matrix, like we defined before, could be written as either I or IN, playing the role of 1. It just produces a 1 along the main diagonals. And we really take this analogy strict in the sense that if we do have an inverse, we write this in. And so the equations above just become A inverse times A equals identity matrix. And then A times A inverse is the identity matrix here, matching the same idea from above. So that's the rundown on what we mean by inverse. We'll take this as our core definition here. And like we mentioned before, some matrices cannot be inverted. We'll either say the matrix is not invertible, which is an okay way to say it. Occasionally the book calls this a singular matrix, and an invertible matrix will be called non-singular. That's kind of a fun, interesting word. Whenever you're using the word singular, it means something that's unusual, something that's kind of rare, something that doesn't happen by chance very often. The reason non-invertible matrices are called singular is if you just write down a random matrix, putting in random digits in all the entries, the odds are it's invertible, it's non-singular. You actually have to arrange things just right to make your matrix be singular, not invertible. So that's kind of interesting language. I usually try to say invertible versus not invertible because it's straightforward, but this does come up in a lot of contexts. So it's just important to be familiar with that language, especially in the homework exercises. So to just practice with all these concepts, here's a quick situation. I have a random matrix A, just a 2 by 2. We want to show A inverse exists, and it's equal to that matrix right here. Well, it could all be a lie. It's our job to show that this is true. So if we're not sure if that's actually the inverse, you probably would want to call it a matrix C, thinking of the definition right above. Then we have two things we need to check. We have to say what happens when we take C times A, and what happens when we take A times C. So this is using the definition in its most literal sense. Our hope is we get the identity matrix twice. If one of them fails to be the identity matrix, then this whole thing is a lie. That's not the inverse at all. Doesn't say A is singular, just means perhaps there is a different inverse matrix, or maybe it really is singular if this doesn't work out. So let's work this out. Multiplying by C says take -7/11, 6/11, 3/11, and -1/11. Multiplied by A, which is 1637 going column-wise. It's kind of a fast multiplication as a 2 by 2 system. So first I'm going to build out column 1. We'll take -7 times 1 plus 3/11, or let me say that better, -7/11 times 1 plus 18/11. So that'll take us to 11/11, which is exactly 1. Then redo. This will be 6/11 plus a negative 6/11 that balances to 0. And that builds out our first column. Then we repeat the row multiplying corresponding entries to get the next column, just focusing on this column here. So this to this will be negative 21 plus this and this is positive 21, balancing to 0. This entry multiplying this is 18/11. Here to here is negative 7/11. So once again, we get 11/11, which is 1. And the identity matrix came back. So that's nice. It looks like C is potentially the inverse. In fact, I think we've hinted at this last class. Theorems later on in section 2.3 will tell us that was actually enough. If you get the identity matrix in just one version, you've found the inverse. But you have to work hard to get to that point. It's a good amount of mathematics. When you first define the inverse, this is what it looks like. And then you have to prove something to get there. That's why we're doing it twice. But that is an honest theorem later on down the road. So if you happen to be aware of it and you just call this good, I'd assume you're thinking of that theorem. You can't be penalized for knowing stuff in this class, in other words. But I'll do it in the strict sense of the definition, being literal as possible, assuming this is as far as we've read into chapter 2. We have to do it the second way. So we'll take A times C going this way, 1637, multiplying by the matrix C again, negative 7/11, 6/11, 3/11, negative 1/11. When this multiplies together, let's check this out carefully. Building column 1, we'll have negative 7/11 plus 18/11. And we've done that several times already. That's 11/11 for a 1. Then here to here is negative 42/11. Suddenly it feels kind of different. But then here to here is positive 42/11. It balances to 0. So far, that looks like it could be the identity matrix. So we continue to go. Here to here is 3/11, minus 3/11, so 0. Then here to here is 18/11. Here to here is minus 7/11, so that's 1 again. And it worked out. This is the identity matrix. And so we've pretty much done this. We've shown A inverse exists, and it equals that matrix right here. So whenever the algebra works out, we get the identity matrix, we can now say, therefore, C was in fact A inverse. And we could have called it that all along if we so chose to. But that's our work getting through this. So far, this also tells us, and A is invertible, or in other words, non-singular, which is just a special way to say ordinary. So this is one thing, again, that's kind of tough about this book. There's lots of ways to say the same thing. You can say it this way, A inverse exists. Or you could say it this way, A is invertible, that's synonymous. Or you could say it a third way, A is non-singular. Either way you say it, it's the same exact concept. I usually say it this way more often than not, but it's important to be familiar with all the different ways this same concept could be expressed. Well, that's the introductory topic with matrix inversion. A key part of this notes is we want to actually find out how to calculate the inverse. This was just thrown at us, so we want to discover how would we compute it if we were just giving the matrix A? Or even better still, how would we know the inverse even exists? How can we detect when the matrix is singular? Or in other words, non-invertible? But any questions at how it works so far? Okay, next theorem is fantastic, and it also has a major drawback. If your matrix is squared, that means it has a chance to be invertible. Our concept for invertibility is only for square matrices. And if it has to be of size 2 by 2, finding the inverse is in fact really, really fast. It's a quick formula. If it's of size 3 by 3, this formula does extend, but in the messiest way possible. There's other things you have to calculate, and it's a hard, computationally expensive way to get through it. So we'll look into another algorithm for inverting matrices that are larger than this size, 3 by 3, 4 by 4, and so on. But here's how it goes. The first key thing is that, and that's kind of a curious little operation. If A times D minus B times C is not zero, that's talking about the main diagonal. Multiply the main diagonal together, subtract the multiplication of the off diagonal, that would be C and B, or B times C in that order. If that's not zero, then automatically A is invertible. And the same construction emerges down here. It's part of the formula. So on face value, it makes sense. If that's our formula for the inverse, we can't have zero right there. And so that's a requirement. It turns out this operation is also really special. If we have size 2 by 2, that's how you calculate what the whole concept of chapter 3 is really all about, the determinant of a matrix A. If it's of size 3 by 3, the formula changes, but in a way that we can track and we can still do by hand in a pretty reasonable way. The only problem is it becomes kind of a combinatorial explosion where the computation for 3 by 3, 4 by 4, 50 by 50, and so on grows really, really fast. We'll explore those details later in chapter 3. But so far, this is an interesting concept. If your matrix is of size 2 by 2, the determinant of A, we'll mention that quite a bit in chapter 2, is just this multiplication, main diagonal times off diagonal. We place the determinant of A there, and the entries of the matrix also change. Hope that's the right color. So what was the main diagonal, A and D, have swapped. So we just do a complete swap of your main diagonal. The determinant's going to multiply these, and your off diagonal, we don't swap it, we just multiply by -1. So that's the complete recipe for calculating the inverse of size 2 by 2. And it tells us a lot. It tells us when it's invertible, and in case it is, what the formula should be. Well, any questions at all, folks, looking into that formula? Okay, let's play with it right away. We have two matrices to work this on. First, with the matrix A, the very first thing we'd want to calculate is determinant A. It's part of the formula for the inverse, and it's going to tell us if it's invertible or in the first place. So we'll take 1 times 12 minus 4 by 3, 12, comes out as 0. And so, well, that's kind of interesting. It says if it's not 0, then A is invertible. The fact that we got 0 immediately tells us this shows A inverse does not exist. Or if you prefer, you could say A is singular. So that's a pretty fast computation right away. By the way, if you stare at the columns of A, there's something you could say about those columns. A wouldn't notice anything interesting about that column versus that column.
The second column is 3 times larger than the first.
Yeah, good call. That tells us right away that these columns are linearly dependent. That happens to be not a coincidence. We can't invert this matrix because the columns are linearly dependent. So let's tie in that thought right here. These thoughts are all coming together quite quickly, so we might as well look into those preview concepts. So A is singular, then this occurs if and only if the columns of A, they're multiples of each other, like you said. Take column 1 times 3, you get column 2. And so the punchline is the columns of A are linearly dependent. So we can now tie those kind of concepts together. The determinant was just another way to see that. you can connect this thought as well. The determinant of A being 0 is the same concept as the columns being linearly dependent, which is the same concept of A is non-invertible, it's singular. So we have a long string of concepts already just growing and combining to each other. And that's going to be the content of section 2.3, the invertible matrix theorem, to put all these thoughts, all this kind of stuff in one spot. But that finalizes the matrix A. Let's try it again with matrix B to see what's going on. Determinant of B, we take the product of the main diagonal. It'll start as a 1 times 0, so we'll get 0 minus product of the off diagonal is going to be 4 by 3 for a 12. This comes out as negative 12, which is not 0. And so this alone implies directly B inverse exists. Then this formula right here just tells us how to calculate B inverse. B inverse is going to be first 1 over the determinant we just calculated. So 1 over negative 12. You have to be really careful on the entries. So go to the main diagonal, see the formula above on how we went from here to here. Swap the entries on the main diagonal, so it goes 0, 1. Multiply the entries on the off diagonal by negative 1, so that we get a negative 4, negative 3. And now we just have to crank this out, multiply by negative 1/12, and we get 0, 1/3. This is a scalar multiplication, so we're just multiplying all the entries. This entry here will be a 1/4, and then a negative 1/12. So there it is, that's our inverse of the matrix B. Looking into the matrix B, thinking of these comments we wrote on the right, the determinant was not 0. Columns are not linearly dependent. To go from entry 1 to entry 1 here to here, you'd have to multiply by 3. But multiplying this 4 by 3 would have given us a 12. So that 0 gives us linearly independent columns. So A is non-singular invertible, occurs if and only if the columns are linearly independent, like in this case, which occurs if and only if the determinant is not equal to 0. So if you negate all these statements, you have logical equivalence again from the same concepts, all three matching up. So that's our quick look into how to get to the inverse of a matrix. We want to expand this up so that we convert 3 by 3 matrices and look into other theorems related to the matrix inverse as well throughout the notes. Any questions at all, folks, getting through example 2? Okay, so far matrix inversion just looks like it's a handy formula, but keep in mind, this is a big warning. This breaks down for 3 by 3 matrices and beyond. But here is the next interesting concept. One good use of a matrix inversion is that we have a nice way to solve this equation. If we have an equation AX equals B, we can use row operations to reduce this and get the solution. But if we know that the matrix A was invertible, we have an alternate way to actually find the solution to this system of equations, written here in its matrix form. So we'll assume A is an invertible matrix. Then for any B that you choose, this is the set of values on the right-hand sides of all the equations if you wrote them all out as a system of equations. There'll always be a unique solution. And the unique solution is also specified in this way. X equals A inverse times B. Example 3 says to prove theorem 5, but really this is kind of a type of homework problem that we're going to see as well in the notes. All we're doing is we're taking this equation and solving it for x. Kind of like how we would solve an equation 3x equals 7 for x. Just the trouble here is that it's a matrix equation, whereas this was a scalar equation. So some of the problems in the homework are doing this kind of equation solving. Here's how this would go. Copy down AX equals B. Then we're told A is invertible, so we know A inverse exists. A inverse exists. And this is going to allow us to take this equation here, and we have to multiply it in a very specific way. For example, we can't necessarily go like this. AX times A inverse equals, that was an inverse there, B times A inverse. This whole equation would be just totally undefined for multiple reasons. If we look into the right-hand side, B is a vector in Rn, so it's 1 by n. Actually, this looks like it's not quite right. Let me try again. B is a vector in Rn, which means it has n entries. It's n by 1. A is an n by n matrix, so it's n by n. And this tells us the right-hand side is undefined. And so is the left-hand side at the same time. So when we multiply, we have to do it in a very specific way. We have to pre-multiply by the inverse. So it would look like this. A inverse times AX equals A inverse times B. Now we can start using properties of matrix multiplication. We don't have commutativity, so putting A inverse here just ruins the whole equation. You can't move it over to the left-hand side. You have to start by pre-multiplying both sides on the left by A inverse. But then what we do have for properties is, thankfully, associativity. There are algebraic structures that don't have associativity, so thank goodness we're not in that kind of strange abstract landscape. This kind of algebra still works out. And this is just an organizing step. It reminds us if we take A inverse times A, see the notes above, the whole punchline to that is you get the identity matrix. And the identity matrix times any other matrix is just like multiplying by 1. So back down here, this becomes the identity matrix times X equals A inverse times B. Well, this is an n by n matrix. This is of size n by 1, so this is nice and defined. And the identity matrix times a vector also just returns back that vector itself. So X equals A inverse times B. And we did it, folks. Even though it had interesting instructions, it said we're proving something, the proof was just to show how to do the algebra when we're dealing with matrix equations. We needed an inverse because we couldn't divide by A. The concept is pre-multiply by the inverse of A, if it exists. If that inverse doesn't exist, if this part is false, well, having a solution for all B and Rn might not be true. This could be inconsistent. And so there's no direct formula for an equation. If there's a potential, it's inconsistent for some value of B. Well, any questions at all, folks, on running through this problem? Okay, I think the big question I would have doing this is, we're going to do it again down here. We're going to solve a system of equations by using A inverse for the right matrix A. Why do it that way? Because you could just take this, row reduce it, and get an answer out really fast. Well, the reason we have to do it this way, these are instructions we're going to see again on exam 3, as well as our upcoming homework assignment in section 2.2. The reason we have to do it this way is, well, 2 reasons, just to practice the concept, but also because the concept is bona fide a great one. Here's a reason that you would want this kind of process. Finding the inverse of a matrix is computationally intensive. It takes a lot of work to do. So that means solving a system going from here to here isn't always a good idea, except if you're doing some kind of model building. So if you're looking into something in an applied setting where you're building a model and B changes a lot, maybe you're looking at what effects might have for a different set of forces in a physics situation, but the coefficient matrix A is always the same. That's a reasonable application you could be in. So as you vary the parameter B in this model, you have an immediate solution for every single B once A inverse has been computed. So in those kinds of concepts, in applied settings, doing model building, this is a great approach. Doing the row reduction every time you change B, or row reduction every time you switch those two values right here, that could in fact be the computationally intensive thing if we're changing this for many, many different vectors, potentially on a continuum. So it's a great concept. It's really for applied settings most of all. And so we'll practice it here just to see how it goes. So first thing we have to do is take the system of equations. Imagine this came from some kind of physics problem. Analyzing forces is a good one to think about. First thing we want to do is rewrite it as a matrix equation. AX equals B. A is going to be a matrix of coefficients coming from the system here. So we can rewrite this as, for column 1, we'll get a 1, 4. From column 2, you'll get a 3, 1. The vector x here becomes just the variables in the problem, x1, x2, and the vector b in the matrix equation is just the right-hand sides, so 0 and 1. So this is our matrix A. This is the column vector B that we're working on. And that's where all the information comes from. Some of these are kind of hard to highlight because there's no 1 there. So imagine a 1 being right there as a coefficient. So if we're going to solve this using a matrix inverse, the last problem was just telling us exactly what that solution would look like. So the solution is x equals A inverse times B. So we have to find A inverse as well, but that's a big part of these notes anyways. So it's a second look at that topic. Let's start next after writing this down by finding A inverse. Let's also see if it's invertible in the first place. If this is an implied setting, we definitely would want to know that information. The determinant of A is the product of the main diagonal, so 1 times 1. Minus the product of the off diagonal, so 4 times 3. That's 1 minus 12, so it's negative 11. And this tells us A inverse exists. So this problem can be solved. We can find the A inverse and put it here. A inverse is going to be first 1 over the determinant, or the reciprocal of the determinant. Then the number game we play on this matrix is swap the main diagonal. It's kind of foolproof in a certain sense, right? So if it's 1, 1, just imagine you swap them. Negate the off diagonal, so multiply these by negative 1. So negative 4, negative 3. And actually in this problem, I would leave the scalar multiplication here and not simplify this matrix. Turns out it's easier to take A inverse times B if you take this times the vector B, then multiply the resulting column vector by the scalar. So putting it all together, x is going to be equal to, once I can switch that out, there we go, A inverse, which is negative 1 11th times 1 negative 4, negative 3 1, multiplied by the vector b, which came from here, or we rewrote it down over here, 0 1. And then we're pretty much there. X equals negative 1 11th of, take the matrix times the vector, row 1 multiplying corresponding entries in the column vector give us 0 minus 3. Same operation here, we'll get 0 plus 1, so 1. Now is a good time to do the scalar multiplications. It made it a little bit cleaner because we're not looking at as many fractions, but honestly, it's going to be just about as fast either way. So this becomes positive 3 11ths, negative 1 11th. If we did the row reduction up here, you would probably have solved this problem in a third of the amount of time, and would have gotten the same exact result. Again, think of this as valuable if we are putting in infinitely different options here, almost like a slider, changing that vector b to see what happens to the solution x. If that's something we're trying to explore, the A inverse matrix makes all of that very, very computationally efficient. So that's one good use for matrix inversion. It can help for these kind of exploratory system solving. Any questions at all, folks, getting through this one? Okay, so we see how to invert a 2 by 2 matrix. We have some properties for matrix inversion related to equation solving. And here's the next nice theorem that gives us good properties when it comes to matrix inversions. some of these properties might feel like deja vu. If you have A as an invertible matrix, A inverse is also invertible, so that's a good property all in its own. And that's just because if you multiply in this way and just change the role of which one you're studying, this matrix multiplying into A inverse got us the identity, and this matrix A multiplying into A inverse got us the identity. So A inverse is the inverse of A, and A is the inverse of A inverse. There's just two ways to look at this same exact concept. In fact, let's take this with us as we go. As we study the next properties down below here. Sorry, that was scrolling a little too fast. Okay, we can just park that there, I think. Okay, so inverting the inverse, the punchline is you just get the matrix A. And the related topic that makes it feel like deja vu is that's essentially what we were looking into transposes. If you transpose a matrix A and then transpose it a second time, it returns that same matrix A. So the same exact concept works with inverses, and that's kind of nice whenever we see some parallelism. Makes it easier to memorize both sets of concepts. The next one is, if A and B are both invertible matrices of the same size, n by n, then you can multiply two invertible matrices together, and the resulting product is also invertible. So that's a wonderful product. If it's invertible, we need a formula for that, and the inverse is the product of the inverse of AB is a product of the inverses of A and inverses of B in reverse order. In other words, A times B inverse is B inverse times A inverse, which should feel like part D for the transpose law. A times B transpose is the product of the transposes in reverse order. So really strong parallelism there, which is kind of nice. That's about where it ends, but parts A and parts D down here go really well with parts A and B here as well. You know, it doesn't hurt to write that in just to tie that concept in. A transpose transpose is the concept going along with A, and AB transpose, including B transpose times A transpose, is a concept that matches with part B. Then finally, transpose and inverses can go together. A transpose inverse is the inverse of A transpose. That's kind of hard to say. Well, we're going to look into verifying this part right here on part B, that A times B inverse is B inverse times A inverse. If you're curious on how this one goes, pretty much all you'd be using is part D again to make that proof work for you. These are actually pretty tricky proofs in a certain sense. In fact, to make this work for us, let's take the different definition for inverses. Let's focus on this one. Once the red dot is out of there. Feels ominous to have more than one red dot looking at us. Okay, so this is a kind of algebra problem as well, but I honestly feel like it's challenging in a real sense. Here's how any kind of problem like this would always go. Verify that A times B inverse is this, is telling us this whole thing right here is playing the role of C down here on the original definition. So that's our matrix C that we're going to test to see if we get the inverse. Just to make that concrete, you could label it as C if you'd like. And AB inverse, that's going to be playing the role of, ran out of colors here, just A itself in those two spots. So to see if this is the right formula that we're going to verify, we have to take A times B, post multiply it, or let's go with this one first, pre-multiply it by the matrix C. Then we have to be able to swap it around. In this case, take the matrix A times B, post multiply it by the matrix C. So we're using this definition of matrix inverse in the most verbatim literal way possible, just to see how this tracks. once we have this all set, really just a matter of multiplying things out and seeing what happens. First, I'll undo the substitution for C. C equals B inverse times A inverse. Parentheses here can be dropped due to associativity of multiplication. So we can go A times B. If we'd like, we could reassociate. This right here is just the identity matrix in the middle, A times A inverse. So this becomes B inverse times the identity matrix times B. So the identity matrix is nice when it shows up. It means it just essentially cancels out. I times B here is just the matrix B, or going the other way, B inverse times I is just B inverse. So this becomes B inverse times B. That means the identity matrix comes out another time, and that's what we're trying to show. Pre-multiplying by the matrix C, which happens to be B inverse times A inverse, the product of the inverse of A and B in reverse order, gave us the identity matrix I. But it has to also work down here. If it breaks here, something really funky is going on with algebra. We'd have to go back to the drawing board on this. So we're testing it out a second time. But any questions at all, folks, on how we formed this equation through the definition or worked through it? Okay, I feel like this is, again, for me, it's really tricky because you take a definition like this that already uses the matrix A once, but you're using this as your whole new matrix A. For me, it's not easy to see without matching up the colors or just thinking and staring at it really, really hard. So the color correspondence of what is acting as what is the difficult thing about this, getting all those things acting as the correct role. So on this portion right here, A times B is playing the role of just the A here. C is the thing that we're trying to test as being the inverse. This becomes A times B times, unpacking C, undoing the substitution, it's B inverse times A inverse. And that's where the algebraic miracle occurs. Right in the middle, we can associate once more. B inverse times B, we've already done that once on this page. That's just the identity matrix. So that's A times the identity matrix times A inverse, which means it's just A times A inverse, and we know that to be the identity matrix again. So that does it for us, folks. By going through the definition in the most verbatim, strictest way possible, this shows the inverse of AB is B inverse times A inverse, and it also showed something more. If you're looking into this, it said that so is AB. If A and B are invertible matrices, we just proved as well by going through both of those computations that part of the statement. A times B is also invertible because we found the right matrix C to multiply post and pre to get the identity matrix. So we did more than it really shows on paper on the first look. So the inverse of AB is B inverse times A inverse. And so AB is invertible. So that's the rundown on getting through that problem. I'm going to leave this definition parked right here because, again, it shows how we correspond to the statement here, working through the definition, getting the identity matrix, proving the result. Well, any questions at all getting through that part B on this one? Okay, this one's definitely not as nice as doing this kind of problem. Stuff like this might be fair game in an exam setting. Something like this, I feel like this is an okay as a homework problem, but this isn't meant to be a proof-based course. So I think this would be kind of out of appropriate land for an exam question, but it's something good to study, helps us learn the definition. This could qualify as a decent homework style problem. If you're doing something like this one right here, it's really the same kind of concept. You just have to also pair it with part D from theorem 3, and that's section 2.1. But let's go off to less extreme things. We still have other concepts we want to get to, like inverting a 3x3 matrix or a 4x4 matrix, and so on. So here are the concepts that are going to help us work all those ideas. So first theorem 7 is the major tool. In fact, we were making these observations when we inverted our first matrix. When the matrix was invertible, the columns were linearly independent, which means there'd be a pivot in every single column. But our matrices are also square, so that means there's also a pivot in every single row as well. But that's just the long form way of saying, if your matrix is invertible, this occurs if and only if it's row equivalent to the n by n identity matrix. And we always like saying this in a statement of a theorem. It tells us the logic is reversible. If you row reduce A and it becomes row equivalent to the identity matrix, it tells you it's invertible, and vice versa. If it is invertible, it'll be row equivalent to IN. There's a bigger part of this theorem that's also relevant to us. When you take A and row reduce it to IN, any sequence of elementary row operations that reduce A to the identity matrix also will transform the identity matrix into the inverse. And that's essentially our algorithm. It's just stated in a more concrete way here. So in order to find A inverse by hand, when this is of size 3x3, for 2x2 it still works, but it's just faster to use theorem 4 in this chapter. What we do is we take A, augment it with the identity matrix, start row reducing A. We know A is going to be row equivalent to the identity matrix, so that'll emerge here. But this highlight statement tells us the identity matrix that was augmented will become A inverse. So that's our major tool. So upon row reducing this, we get our A inverse. The downside is if you're row reducing a 3x3 matrix and you augment it, it's now a 3x6 matrix. So that's the downside. But the upside is we have a nice by hand algorithm for computing the inverse. That's exactly what example 6 says. Find the inverse of this. So let's try it out. First thing we do is we take A and we augment it by something large, the 3x3 identity matrix. So we've often augmented by a single column vector, but you can augment by any appropriate size matrix. So A copies in column-wise 1, 1, -6, -1, 0, 2, 0, -1, 3. Then we just put in the identity matrix. It goes 1, 0, 0, 0, 1, 0, 0, 0, 1. Now, lots of row reduction on this. Really, it's not too terrible, except we also are tracking what happens to the identity matrix. As we row reduce the original matrix A to the identity gets transformed into the inverse. So here's how it's going to start. I'm going to copy in the entirety of row 1. 1, -1, 0, 1, 0, 0. Multiply row 1 by -1, add it to row 2, and we'll get 0, 1, -1, -1 again, 1, and 0. Next, take 6 times row 1, add it to row 3. Let me know if any of my numbers go sideways. There's a lot of information to track. 6 times here, added to row 3 will give us a 0. -6 plus 2, so -4. 3 on this one, the zeros are handy. 6 plus 0 for a 6. And then the zeros just tell us copy the entries below, 0, 1. So on to the next step. This column is already the first column of that 3x3 identity matrix, so we're on our way. Working in column 2, we just need to eliminate reduce to 0 entries above and below. So that says when we write down the next step, we should just copy in row 2. 0, 1, -1, -1, 1, 0. Let me just double check those. Okay. Anywhere there's a 0, nothing can change above and below. So I'll copy in these values as well. 1, 0, 0 there. Last column is 0, 0, 1. So only changes are going to be from these entries here. Looking at the prior matrix, we're just going to take row 2, add to row 1, replacing row 1. So we'll get a 0, -1, 0, and a 1. Next, we're going to multiply this row 2 by 4, add it to the row 3 below. So we'll get a 0 to start. -4 plus 3, so a -1. -4 plus 6, so it's going to be a +2. Then 4 plus 0 for a 4. So far so good. We have columns 1 and 2 are the columns of the 3 by 3 identity matrix. We just have to fix this column here. And this is a lot of writing. So I think a lot of people, if you were doing this by paper, you know that's got to be a +1, right? Let's take a little shortcut on this one. I don't think we've ever done this on the notes. Here's how you'll know we took this kind of shortcut. Let's multiply by -1 right here, right now as it sits. So I'll convey it this way. Purple means we did an extra operation. That's a +1 now, a -2, a -4, and a -1. This just saves us a load of time because writing down a 3 by 6 matrix is going to make your hand tired after a while. But does that make sense to folks taking in that shortcut? Okay, with that shortcut in play, we're now nearly done. We're just going to pivot off of this entry in column 3 by adding the third row to row 2 and row 1, replacing them. So this is the last step in the row reduction. First, I'll copy in the columns that can't change, 1, 0, 0, 0, 1, 0. All the rest of the columns will change. So now I'm just going to write in the rest of row 3, 1, -2, -4, -1. Now take this row, add it to the row above, and we'll get 0, -3, -3, -1. Take row 3, add it to row 1, and we'll get 0. I forgot the 0 here. Let me try again. Here to here will give us a 0, -2. Hang on. I think I got mixed up on my zeros. Let me try one more time. Third time's a charm on this. This entry added to this entry will give me a 0 there. This entry to this entry is -2. My eyes just lost a place on the page, it looks like. Here to here will give us a -3. And then finally a -1. At that last step, I would take into the fact that we've augmented. And we're nearly done. But there's still one more thing we have to do. When it says compute the A inverse of A, I need to know that you know what part of this, because it's a big mess, is the inverse. So standard reminder is don't forget to state the conclusion. The conclusion is finally that A inverse is this matrix sitting right here. -2, -3, -2, -3, -3, -4, -1, -1, -1. So my claim is, if you take this matrix, multiply by this one above, either pre or post multiply, you'll get the identity matrix back. And if this was an exam 3 question and you have a little bit of extra time, not a bad thing to do because it's easy to make a simple mistake here somewhere in the row reduction. But any questions at all, folks, computing that 3 by 3 inverse? Okay, well, this is our quick algorithm on making that happen. Lots of things that we can say about this is the instructions are really important as well. If it says compute the inverse, we knew that this was the right thing to launch right into because the inverse would exist. But if the instructions change a little bit and it says, explain why A is singular, you would never want to use that algorithm. It would be just a waste of effort. Showing that A is singular just means row reduce A, show that it doesn't become the identity matrix. Or there's a lot of other things we're going to be able to say down the line. If you know how to take the 3 by 3 determinant, you could go that route. It's going to be 0. If you're thinking in terms of linear independence and dependence, if the matrix is singular, these columns should be linearly dependent. But how did we even test that? We checked how many pivots were in the columns. That's the same thing as trying to reduce it to the identity matrix. But reducing to the identity matrix, that's computationally more intense than we need as well. You can really reduce the effort here by doing the following. First, A is singular means A inverse does not exist. Sure, it also means A is not row equivalent to the n by n identity matrix. But at the same time, you could just reduce this concept to saying A does not have a pivot in every column. That's the main punchline. And because we're just looking into the pivots, you don't need to take this to reduced row echelon form trying to get it to the identity matrix. All you need for this is echelon form. So let's make that our big comment. We just need echelon form. So no reason to augment it. That's a lot of effort that you don't need to show on this. You're not going to get the inverse either way. And no reason to try to take it to reduced echelon form. Ordinary echelon form is enough to show where all the pivots are. And if we say this is singular, we're expecting 1 or 2 pivots on this. Potentially 0 pivots, but the only way that happens is if they gave us the 0 matrix straight out. So there's going to be at least 1 pivot on this thing. So take A, just immediately start row reducing it. Column 1 goes 1, 2, 0. Multiply row, I said column 1, row 1 goes 1, 2, 0. Multiply row 1 by -3, adding to row 2, and we'll obtain 0, -6 minus 1 for -7. And no change here, 2 copies in. Double row 1, add to row 3 to get 0. 4 plus 3 for a 7. No change here, so copy down the -2. And now you could probably see the pivots already just on this matrix. Let's take it all the way down to echelon form. It goes 1, 2, 0. Now take row 2, add to row 3. I should copy in row 2 first. Okay, now add the rows together. We get 0, 0, 0. We have a pivot in columns 1, column 2, but not 3 pivots. So we could tie together this concept up here and say A is 3 by 3 with only 2 pivots. And so A is not row equivalent to the identity matrix. How would you say that? You'd write row equivalent and put in a slash like that. So now it's not row equivalent. I don't think we've ever defined that on paper, so we should say that here. This whole symbol means not row equivalent. So if you only have 2 pivots, you can never get to the n by n identity matrix. Let me make that specific. This is the 3 by 3 identity matrix. So A inverse does not exist. You can end the write-up there, or you could say, so A is singular. Again, that would just be synonymous with saying the inverse does not exist. So it's a really nice theorem. It tells us at a glance when the inverse doesn't exist. We also use this theorem to build out this row reduction here to even compute the inverse when it does exist. But the form of the question is going to tell you how much effort you really have to put into this one. This one is just a basic get it to echelon form type of problem to reveal the pivots and then make a conclusion. Well, any last questions, folks, on getting through that example? Okay, well, we've done most of the main concepts that we want to get through on these notes. We can convert now any size matrix using different algorithms. Last couple concepts we'll take a look into is relating this to linear transformations. In fact, we've kind of already talked about this in a certain sense. there's a synonym here. When you say T is invertible, it just means it's 1-to-1 and onto. And this is the same thing as saying T is an isomorphism. There's many kinds of isomorphisms. So if you want to be specific, you might say T is a linear isomorphism. Well, hang on. That's only if you said the transformation was linear right here. So I guess that's not the perfect connection at all. So if it's not a linear transformation, then this is a good definition. T is invertible. Let's write this in above here. If T is linear, then this is turning into a longer sentence than I imagined. Let's make sure it's accurate here. If T is linear and invertible, then this is the same concept of T being a linear isomorphism. But here it didn't say anything about linearity. So for any transformation, invertibility just means 1-to-1 and onto. But we're looking into linear transformations. And notice another change here. The definition was built to be as general as possible. I just forgot. I was excited about this part right here. Sometimes that means isomorphisms. But not this time. This is just a generic transformation, and it's going from Rn into Rm. If we look into a linear transformation, if T is linear, and we also want it to be 1-to-1 and onto, then the codomain and the domain space, I said that backwards, the domain and the codomain space has to be of the same exact size. So let's say that the transformation T is a linear one. A is its standard matrix. Assume T is invertible, and that right out of the gate tells us if T is invertible, then T is 1-to-1 and onto. Example 8 is now telling us T being invertible is the same concept as A being invertible, where A is the standard matrix. Really, it's just a quick way to connect these dots. If we go back to section 1.9, this is part of the notes on the exam too. Let me blow that up. Oh, darn it. Blow that up a little bit more. Forget that scrolls when you make things bigger. There we go. So if we say that T is invertible, then the definition above says T is 1-to-1 and onto. But if T is 1-to-1, the columns are linearly dependent, which would mean there's a pivot in every column of A. Actually, that's enough for us to show that A is row equivalent to the identity matrix, because A is a square matrix of size n by n. But there's two things here as well. If T is invertible, that means it's also onto, back here in theorem 12 from 1.9, if T is onto, then the columns of A span Rm, where A is a standard matrix. That just tells us there's a pivot in every row. But we already had that from free on part C down below here, because if there's a pivot in every column and the matrix is square, there must be a pivot in every row at the same time. So let's convey all those thoughts on paper. There's a lot to say. A is a square n by n matrix. That came from the size of the codomain and the domain. Next, we can connect that thought with T is invertible. Means T is 1-to-1, or injective if you liked that way of saying it. Then we can connect that dot with the theorem down below here we were citing, theorem 12 of chapter 1. Let's just write it down on paper. By theorem 12 of chapter 1, now we're talking about the standard matrix A through that theorem. The columns of A are linearly independent. There's more thoughts to connect, but really already here, it's not a bridge too far to say if the columns of A are linearly independent, A is automatically row equivalent to the n by n identity matrix right at this step. But let's connect the thoughts even more. The columns of A are linearly independent. And so there is a pivot in every column of A. So let's get to the punchline. The punchline was if you define a transformation T like this, and it's linear, there will always be a standard matrix, meaning T of X is equal to A times X. For any vector X, we could just do matrix multiplication that way. But if T is invertible, so is A at the same exact time. That's kind of a nice, interesting connection. So if there's a pivot in every column, we can now say, therefore, A is now row equivalent to the n by n identity matrix. And this occurs if and only if A inverse exists. So that's what we wanted to show. T being invertible means the standard matrix A is invertible at the same exact time. It'd be weird if it wasn't, but showing it all come together is quite a bit of writing on this one. Well, example 8 is kind of a heavy concept, but this is something that we're going to return to in the next section notes, 2.3. Any questions at the moment before we try out the last example of these notes? Okay, well, we're nearly there. And here's the last one. There's a similar problem just like this one in the homework as well. We have that the matrix P is invertible, and the matrix A is defined to be P times B times P inverse. Our objective is to solve for the matrix B. Really, this is just another example. We saw another one in the notes where we're just trying to get used to the matrix algebra in equation solving. So the statement for the homework exercise is when you do these to show all steps so that you can get the practice on what do the steps really look like, with pre-multiplying and post-multiplying being the major concepts. But actually, this weird-looking equation turns out to be extremely important. This is called a similarity transformation. And this is something we're going to take a look into in chapter 5. We're going to look into eigenvalues, eigenvectors, and a concept called diagonalization, where this matrix B is going to be a diagonal one containing all the eigenvalues. So this is just our first look at that kind of weird matrix equation. Really, you can also think of these as a matrix A factors in a particularly useful way if it meets the right kind of requirements. In fact, if it doesn't factor in this kind of way, in chapter 5, we'll call the matrix defective. And that's kind of a profound way to refer to a matrix. This is just our first look, and our goal is to solve for the matrix B in terms of A. First thing we'll do is write down A equals, give it a little bit of space around A, P times B times P inverse. What we know about this setup is P is invertible, which makes sense. We put P inverse there, so it's got to be invertible. If we want to solve for the matrix A, we can post-multiply by P here. But it means we have to do the complete analogous thing on the right-hand side. You could do these in step by step if you like, but some people would possibly want to pre-multiply by P inverse here. You can do that and just multiply P inverse here. But then you're required to multiply by P inverse in this location. The order of multiplication does matter, so we have to form it in exactly that kind of way. So keep this correspondence here to here and here to here. Then you can associate in this way. Matrix multiplication is associative. So this becomes P inverse times A times P equals, big punchline of these notes is when you multiply an inverse with the matrix, you get the identity back. Times B times the identity matrix again. And the other big concept is a matrix B times the identity matrix, or even a column vector X times the identity matrix. You're multiplying by 1 as an analogous concept. So this just becomes P inverse A times P equals B. Almost looks like this equation, but the inverses have moved to different spots. Well, any questions at all, folks, doing that last equation solving there? Oh, there's more. Forgot I have more stuff on these notes. It looks like it's optional reading though, but it looks like we got to the end on these ones. What the optional reading is all about is Theorem 4 is a pretty unusual theorem. It does a lot all at once. And proving this theorem is, it's straightforward in a certain sense. There might be other interesting, clever proofs, but if you're curious about this kind of proof, I think they're kind of cool in a way. This is what it looks like using just the brute force algebra to prove it's the right thing by cranking it out step by step. Some people consider these to be ugly proofs because there's lots of stuff you have to write down. If you like this kind of stuff to see how it goes down, just multiplying things through, showing you have the right thing, saying that this has to result in an identity matrix, looks like that, then you have a system of equations to get through, then that's what the proof looks like. But it's optional reading. It's just to show how would you prove theorem 4 if you really had to, and you're not going to do it in the world's most cleverest way. You're just going to crank it out. So we reached the end of the notes. Really, chapter 2 is kind of a small chapter. Chapter 3 will be similar as well. And the capstone to the entirety of chapter 2 is going to be section 2.3. We don't have a lot of time to really get into it, but the idea with this section right here is it's in a certain sense a restrictive extension of this theorem. I think it was a section 1.4. In this section, we have an awesome theorem that we've used over and over again. And it continues to be a really awesome theorem. It's 4 concepts that are logically equivalent, and the pivot being in every row is the way we get a hook into this theorem. It's general in the sense the matrices do not have to be square. So that's what's really nice about theorem 4. But it is restrictive. You can't really put in a whole bunch of more concepts here than what we see. I can't throw linear independence if I make it general and by n. So this theorem is restrictive. This is only square matrices. But if you restrict to only square matrices, every one of these concepts becomes logically equivalent. They're all going to be true at the same time, or they're all going to be false at the same time, just like these statements were all logically equivalent. A being invertible is the top thing on the list right here. And in using this theorem, look at what it has. It has spanning, it has linear independence, it has things about linear transformations. Whole lots of stuff is inside here. The hook to this theorem, the way you can use it the easiest is finding the number of pivots in your matrix A. The next easiest way would just be calculating a determinant. So that's going to be the content we're going to practice when we come back on Thursday's class, working through the invertible matrix theorem. I don't think we have enough time to say too much more about it, though. Any last questions before we call it a day? Okay, so we'll work our way through this, organizing how you can really group these together so it doesn't look like just random letters A through M. There's actual logical grouping. And the cool thing about this theorem is this is one of the theorems that grows. The more concepts we add to this course, and we have several, the longer the list goes. So it gets bigger in chapter 3, chapter 4, chapter 5. This is just what we have so far on the table for it. But have a great afternoon, folks. We'll return to this stuff on our Thursday's class. There you go. Thank you.